So when we talked last time, we introduced the concept of normal and tangential. We had finished up with x and y coordinates and done some examples of that. And then starting into normal tangential. Before we're all done, we're going to get into r and theta, or cylindrical coordinates. And I want to emphasize the fact here that we're not changing the physical problem. We're just changing how we look at it. We're just changing the coordinates that we apply to it. You could take any one of these methods and apply it to a problem, and done correctly, you get the same answer. Although one method or another is probably going to be a lot easier on particular problems. If you've got a problem that's given in x-y coordinate systems, using a normal and tangential will get you the right answer, but it's probably going to be a lot more work. So I want to emphasize we're not changing the physical problem. So in thinking about normal and tangential, let's say that we have something that's going along a path here, a curved path, and you'll notice that the normal and tangential directions change. By definition, the normal always points to the center of curvature. So the positive normal, if we have a center of curvature here, the normal direction points to it. If I have a center of curvature here, the normal direction is pointing to it. So that tells us where the normal is. And the tangential direction is always in the direction of the velocity. When you have a curvilinear motion, you will notice that the velocity is always in the tangential direction. If you've ever had the head fly off of a hammer, or you've ever maybe golfed or something like that, you recognize that relationship, that the velocity is in the tangential direction. For instance, speaking of golf, if we have that golf ball here, and we look at the swing coming down, part of the whole secret of this is timing it right in your swing, right? If you hit it too early in your swing, if you're hitting it up here, you're going to drive the ball into the ground. If you hit it too late in your swing, you're going to drive the ball way up. It's going to be essentially a pop fly in golf, which is probably not a good thing, right? It just gets to the ladies' tees, and that's kind of embarrassing. So, okay, it goes way up in the air. That's cool, but doesn't go very far. And then we could take that to the third dimension, or the third dimension also, and that's your hook or your slice. But it's probably easier just to think about lofting if we're looking in 2 dimensions here. So as we go through this, your author is going to talk about unit vectors in the normal direction. Your author likes to use the symbol U sub n. I like to use the symbol E sub n. Okay, so I'll be using E sub n as the unit vector in the normal direction, and I'll be using E sub t as the unit vector in the tangential direction. Your author will be using U sub n and U sub t, and those are a couple pretty common designations. Whether you see U sub n or you see E sub n, that is the unit vector, so it has a magnitude of 1, and it simply gives the normal direction or the tangential direction if it's E sub t. Now remember that those are changing, so while the magnitude is a constant 1, their direction is changing, and that's going to have implications as we get into the calculus of the problem. So let's look at a particle then moving along this curve here, and let's look at it at this point here. We could say that that's A, and we can look at it sometime later. Why don't I say that this is A prime, if you will. And at A, we would have some velocity in the tangential direction. That velocity is going to be in the E sub t direction. And then perpendicular to that, the tangential and the normal are always mutually perpendicular. We would have the normal direction. That would be going back up the radius of curvature to the center of curvature on this problem. Then sometime later, we come up to this point here, A prime, and it'll have some, maybe the same velocity, maybe different velocity. We'll say that that's velocity v prime, and that's now in the E sub t prime direction, and the normal direction is in the E sub n prime. So a different tangential direction, a different normal direction. And one thing that I'd like to add here is I'd like to look at this arc length of this curve, and say that that arc length is going to be equal to ds, which is rho times d beta. So this angle in here is d beta, and the radius of curvature is rho, so you multiply your radius of curvature by your angle in radians, and that would give you arc length. So you have arc length there. So we should be able now to talk about velocity. We should be able to talk about acceleration. So if I start talking about velocity here, I can say the velocity is, of course, by definition, ds dt. We've seen that for a week or so now, which I could really rewrite if I wanted to as rho, making my substitution for ds. I could say that that was rho, which should be constant, and then d beta dt, right? I could expand this velocity if I wanted to into a vector form and say that it's equal to the magnitude of the velocity, and we know that the velocity is always in the tangential direction. Have you ever seen maybe a head fly off of an axe or something? It always departs in the tangential direction. Probably makes it so you want to always stand in certain places if you're observing someone chopping wood or something. So we know the velocity, the magnitude of the velocity is always in the tangential direction, so we'll append to the magnitude the unit vector for the tangential direction. And we could take this one step further if we wanted to. We could say that this is rho times d beta dt. I could just say that that was beta dot, right? Okay, the time derivative of beta, and then again, give it the tangential direction. Okay, so the velocity is pretty straightforward. It's always in the tangential direction. It's going to have some magnitude, going to be in the tangential direction. Now, if I want to talk about acceleration, things get a little more complicated. I know that the acceleration is going to be equal to the derivative of the velocity, right? So I could say that this was equal to v dot in the tangential direction plus v, the velocity, times e sub t dot. So I just come up and I use this expression, differentiating that the velocity is the magnitude times the unit vector in the tangential direction. So I would have v dot times e sub t plus v times e sub t dot. That's the product rule, right? Now, last time when we were looking at I and j, if we come down here and think of, well, this is an x and this is I and this is y, and it has j, those were fixed, right? So the derivative of the unit vector in the I direction or the x direction, that was 0, right? But these unit vectors are changing direction, so while they have a magnitude of 1, their direction is changing, and we would expect this not to be equal to 0. So, not 0, because its direction is changing. So I guess I had better deal with that. Let me go and look at this e sub t. We'll notice that the e sub t is kind of pointing this way here, and is turned a little bit on that one. So let me bring that to a little more detail. So I'll say that I have e sub t here, okay, from that one. And then I'm going to say a little bit later, I have e sub t, and I've exaggerated a little bit, but we'll have e sub t prime, okay. And then the difference between this, let's call this d e sub t, okay, the change in e sub t. And this angle in here, that's going to be our d beta. Okay, would be the same angle that we have over there. So if I talk about the magnitude of d e sub t, so going out here and let's just look at the magnitude of that thing, d e sub t, what's that going to be? Well, it would really be equal to the magnitude of e sub t times d beta, wouldn't it? Because we're just looking at the arc length there. So if I take the distance here, which would be the magnitude of e sub t, and multiply that by the angle that goes through here in radians, I would get that. Now what's the magnitude of e sub t? Yeah, that's 1, isn't it? Okay, so I can say that this is dB. So that's worth hanging on to. Now if I look at the direction, if I look at the direction of d e sub t, as this d beta gets smaller and smaller, I could say that that direction for d e sub t is given by something that's perpendicular to e sub t, right? I mean, even the drawing that I've shown here, d e sub t is pretty close to perpendicular to e sub t, right? And as d beta approaches 0, it's going to become perpendicular. So what's perpendicular to e sub t? Is given by E sub n, isn't it? By definition, E sub n is perpendicular. So I could put those two together and say then that d E sub t is equal to E sub n dB. Okay? Or that if I did this with a derivative with respect to time, I could put dt there and dt there, and I could go one step further and say that I have E sub t dot, which is this, the time derivative, is equal to beta dot, the time derivative of that, times what? E sub n? So now I have what that is, right? So I can say that my acceleration, A is going to be equal to v dot in the tangential direction. So that's just your change in velocity. If you're going around this curve and you're not changing velocity, that term would be 0. There's nothing wrong with one of these terms being equal to 0. And then you're going to add to it the velocity times E sub t dot, which is equal to what? Beta dot E sub n. So I'll have the velocity v times beta dot E sub n. So v times beta dot, do we know what beta dot is? Yeah, back from up here, I recognize that this was equal to v, wasn't it? So I have v is equal to rho times beta dot. So what's beta dot? V over rho. Okay. Now let's separate this here. That comes from there. So I make the substitution, and we can say then that the acceleration is equal to v dot in the tangential direction plus, if I have v times v over rho, that's going to give me v squared over rho, isn't it? And that will be in the normal direction. Okay. So that's worth a box. So we have our velocity up here that is just equal to the magnitude of the velocity in the tangential direction. It's pretty straightforward. The velocity is always in the tangential direction. And then a little more difficult here, the acceleration. The acceleration has two components. It would be the change in the velocity. So if you're going around a curve and you're changing your velocity, of course you would have a acceleration in the tangential direction. But even if you're going around the curve with a constant velocity, because you're changing direction, you experience another acceleration. You experience a normal acceleration. This is what people confuse with centrifugal acceleration, right? That's a term we won't be dealing with. You'll have a centripetal force, but your acceleration is, well, you'll have a centripetal acceleration. You're not going to have a centrifugal force. So that's that v squared over rho term. And we'll talk a lot more about the relationship of that with force. There's always that force that people want to put in there to describe things. Remember, we're not talking about force yet because we're still just in kinematics. We've got to let 100 years of history go by, and then we can talk about kinetics and dealing with force. But suffice to say, you've probably seen in physics that the acceleration has two pieces. The change in velocity, that's in the tangential direction, and then by virtue of it going around a curve, by virtue of it changing direction, you have a normal piece, v squared over rho. Are there questions with that? Well, let's look at some common cases that will lead us into some examples. So if I talk about a special case of circular motion, so I've got this particle revolving around a circle, and this is not much of a circle. But if it's moving around this circle, so let's say it's going clockwise around this circle, the circle has some radius r, it would have some tangential direction and some normal direction. And because the radius is equal to a constant value r, I'm just going to change my variables. So the velocity is equal to r times theta dot. If someone tells you the angular rate theta dot, which is just going to be radians per second, you take radians per second and you multiply by r, you're going to get distance per second. That would be a velocity term, wouldn't it? And then what about the acceleration? Well, we said that there was a normal piece that was v squared over rho. We'll call that v squared over r. And then there was a tangential piece that was v dot. So a lot of times I'll break these up into the tangential piece, which is v dot, And we could even write that as r times theta double dot. You might say, well, what happened to r dot? Well, remember, r is constant, isn't it? R is a constant. Okay. And we're going to spend a lot more time with this when we get into particle or rigid body kinematics up in chapter 16 of the textbook. But theta double dot we could express as omega dot or even alpha. And alpha is going to be the angular acceleration, and that will have units of radians per second squared. Theta dot, of course, would be omega, which is the angular velocity, and that would be radians per second. So if you see someone talking about omega, that's really theta dot, radians per second. That's an angular rate. You can convert RPMs, which is a very common number, into radians per second. And then if you look at angular acceleration, how fast that angular velocity is changing, that's your angular acceleration alpha. So just different ways of expressing these things. We've just taken the equation, the general equations, taken the rho out, put r in, and then put some different symbols for different quantities that we encounter. So let's try an example with this. So let's say that we've got an airplane here. This looks a little more like a rocket, but maybe in your notes you'll do it better justice. So we've got this airplane, and we've taken a snapshot in time. This is at some instant. Okay? At some instant, it has a velocity of 30 meters per second and an acceleration given right there, 14 meters per second squared, that's directed at 75 degrees from the tangential direction. That's 75 degrees from its path. Now, I've made a big deal about this at this given instant. Because this is an instant in time, is the velocity constant? Well, the velocity appears to be a number. It appears to be constant, but remember, this is a snapshot in time, right? Okay, I mean, if you're in a hurry to get to school and you're accelerating hard away from a stop sign or a red light, if we take a snapshot in time, do you have what appears to be a constant velocity? Yeah, I mean, you'll be at 30 miles per hour. Are you accelerating? Absolutely. If you look at a moment on either side of that snapshot in time, it'll be different. So we want to recognize this as not constant. Okay? What else is a good clue for saying that that is not constant? Yeah. If I break up this acceleration, I really have a triangle here, don't I? Okay, and if I draw that triangle, I've got the acceleration in the normal direction, and then I've got the acceleration in the tangential direction. Oops, not the normal. Let's see if I can get rid of this. Oh, here we go. There we go. So I've got some acceleration now in the tangential direction, don't I? Okay. And those two combine. They're, of course, at right angles to each other. Those two combine to give me this acceleration that's given at 14 meters per second squared. And this angle in here would be what, 15? 15 degrees? So that's what we got. If this thing was moving with constant velocity, we would know that which acceleration is 0. So big if the velocity was constant, then the acceleration in the tangential direction would be equal to 0, right? But it is not. Okay, so we know that it is accelerating. We know it's accelerating. So as such, we'd like to find, and I spent some time writing this out, we'd like to find the rate of increase of the plane's speed. What in the world are they asking for there? I mean, this is oftentimes the way things are worded, right? It'd be nice if they just came along and put the symbol in and used the same symbol that we learned in physics or learned in dynamics or whatnot. The rate of increase of the plane's speed. What's that? Acceleration, okay. Can you be more specific? The acceleration in the tangential? Okay, great. So we'd like to find the acceleration in the tangential. Also find the radius of curvature of the path. What's that? Yeah, rho. Okay. Good. Okay, so it would have been a lot easier just to say find a sub t and rho, but that's not the way life is expressed. They always spell it out, and then we have to figure out what that is. So let's see if we can do that. We know that the acceleration in the normal direction is equal to what? Well, right up here. We have these expressions. Well, what do we have? We have velocity and we have the radius of curvature, don't we? So let's say that it's equal to v squared divided by the radius of curvature, rho, which would be what? 14, let's see, do we have a value for it? Yeah, it's going to be 14 meters per second squared times the cosine of 15, which would, you could say that this would certainly be the sine of 75 if you wanted to. That's up to you. Okay. No, I didn't do that right, did I? Yeah, I got that right. And what's that equal to? I mean, that's this whole thing is the acceleration in the normal direction. I just resolved that vectorially. That's the acceleration in the normal direction. And what did we say that was equal to? V squared. What's V going to be? 30 meters per second squared divided by the radius of curvature, rho. Okay? So I can say then that rho, so rho is going to be equal to 30 squared divided by 14 times the cosine of 15. If you look at the units, they will work out. They'll give you rho in terms of meters. And that turns out to be 66.5 meters. Okay? So fairly small radius of curvature for a plane, moving right around that corner. Well, that was the radius of curvature. What about the tangential acceleration? Well, that's even easier, isn't it? The tangential acceleration would just be equal to 14 times the sine of 15 degrees, or if you wanted to say, what, cosine of 75? Which when you run through the math there, that turns out to be equal to 3.62 meters per second squared. 3.62. So indeed, it has a tangential acceleration, so it is accelerating. So there's always a little trick here. When you spell out a problem, there's lots of different ways to spell out a problem, and you can trip people up if you want to. That's usually not a goal. It's to seek greater understanding. But if you say something like the craft's acceleration vector is solely in the normal direction, what have I told you? That it has no tangential acceleration, and as many of you are saying, it has constant velocity, right? Okay? So we're going to read these things for all they're worth. Questions with that problem? Yes? Move it up. I can do that. Like that? Yes?
So isn't if it's moving, the direction is changing?
Yes, it is.
The velocity still technically changing even if it's at constant speed?
If it's moving, it's true. If it's moving, the direction is changing, and the velocity is always in the tangential direction, and that's why you have the normal acceleration, because that direction is always changing. There has to be something pulling around that curve.
For your equation up there for acceleration of normal,
You got 14 meters per second is equal to the cosine of 15.
This should be squared.
Oh, that's
Okay. Any questions? Well, let's try a little bit different one, a land-based problem here. Instead of looking in a horizontal plane, we'll look in a vertical plane. So we've got a truck that's laboring along here. It's going through a dip. I think they have some of these. Isn't Hilo Road down south in Salem? Usually about half the students have done something stupid on Hilo Road. Okay, good. Okay, so again, don't do that for this class. But if you've heard hearsay of people doing crazy things, this might be something you'd try on Hilo Road. We have a dip in the road with a radius of curvature of 100 meters. We've got the truck with its center of mass located at 0.6 meters above the surface of the road, so that's going to affect our radius of curvature. And the truck has some constant velocity as it is going through that dip, through that curve, okay, through that vertical curve. That's what the surveyors will call it. And the person in the truck experiences an acceleration of 0.5 g's. So in addition to the static case, I mean, if you're just sitting in the truck in a parking lot, you would experience acceleration due to your weight, or the truck's weight too. And this would be in addition to that. As you go through a dip in the road, you feel heavy. You're pushed into the seat, right? Okay. That additional weight that you feel, how much you're being pushed into the seat, is an additional half of gravity. So this thing is really pushing down. So what I'd like to do is I'd like to find that velocity. What in the world is the velocity of the truck as it goes through that dip? Well, if v is equal to a constant, we're told that v is equal to a constant, I can say that the acceleration in the tangential direction is equal to what? 0, right? So I can focus my concerns on the acceleration in the normal direction, which is going to be what? V squared, V squared over rho? Or V squared over R? Okay. So if I rearrange this a little bit, maybe I better write this a little cleaner, that the acceleration in the normal direction is V squared over rho, or you could say R. Let's put the values in there. What's the acceleration? 0.5 times g. We're in the metric system, aren't we? So 9.81 meters per second squared is equal to the velocity squared. I don't know that. Divided by the radius of curvature. What's our radius of curvature? Yeah, the radius of curvature is going to be equal to 100 minus 0.6, isn't it? So 99.4 meters. We got everything in meters and seconds, so our units should work out. And when you solve for the velocity, this will turn out to be equal to 22.1 meters per second. Is that right? You want to check that with the calculator? Yeah, 22.1 meters per second, which doesn't mean much to me. If you do some more conversions, you could say 79.4 kilometers per hour. If your car was made in Canada, maybe you go out and look at the speedometer, and that'd give you some idea, which turns out to be 49.4 miles per hour. Now we've got something we can look at. That's a pretty tight dip to be moving through with that kind of velocity. If you've ever watched racing and whatnot, you'll notice that nighttime racing is always fun to watch. I should be more specific, like NASCAR racing or whatnot. Occasionally you see in nighttime racing, what do you see coming out from underneath the cars? Sparks. What's that about? Yeah, in the corner, the car's bottomed out and hit the road, hasn't it? Okay. I suspect this whole truck is going to bottom out the suspension too. Okay. And this is a good problem because it brings us into, why do the civil engineers have to do stuff like this? Well, if we look at this the other way, and we'll look at problems like this when we get into kinetics, talking about staying on the surface of the road. But if you're going to design a bump like this, okay, and you got to get around this. There's a couple things that you have to look at. One, you don't want the car to take a trajectory like that. That'd be usually a bad thing, right? The other is dealing with sight distance, particularly with the lights on the car. If you have the lights doing something like this and you have some poor person here, you can miss them altogether. So design in a road, it's more than just saying, well, I've got to get from this point to this point. You have to start thinking about things like that. And sight distance can also be a problem here. I mean, certainly bottoming out the suspension in a car like we talked about. Also sight distance if your headlights are just shining into here and you have something up here, you can have a problem. Okay. So fairly good problem. Fairly easy problem because we didn't have tangential acceleration, but a good solid problem. Questions with that? No questions? So we've talked about Cartesian coordinates, XY coordinates. We've talked about normal tangential coordinates. We haven't changed the problem. We've just changed the magnifying glass that essentially we're looking at the problem. So I'd like to move on to the last one. Your author calls it cylindrical coordinates. We're not going to necessarily go into the third dimension, so it might be better off to call it polar coordinates. So with polar coordinates, we have a E sub r direction, a radial direction, and an E sub theta direction. You could think of if you were some particle moving along this curve here, at a point in time, you could define your position with r. So if you have some distance r and you have some theta here, you could define where that point is. And again, we're going to use the unit vectors. E sub r is what I'm going to use. Your author likes to use U sub r. E sub theta is what I'm going to use. Your author likes to use U sub theta, but these are unit vectors. Unit vectors, of course, representing the r direction and the theta direction. And just like the normal and tangential direction, these directions are always changing, aren't they? Now, if we look at this at sometimes later, E sub r is changed and E sub theta is changed. And E sub theta is always perpendicular to E sub r. So if I come back to this and I want to try and better define r, if I want to define r vectorially, that would be that distance r in the E sub r direction, right? And then if I want to talk about the velocity v, let's see, the velocity v is just going to be equal to r dot, is that right? So that would be r dot in the E sub r direction plus r E sub r dot. So I could take this r vector, put that into there for the velocity, and by using the proper product rule, I'd come up again needing E sub r dot, wouldn't I? So I'm not going to go through this in as much detail as I did in the normal and tangential, because hopefully we learned quite a bit with it. But if I start out with an E sub r direction here, and then I move to a E sub r prime direction, E sub r prime, this difference here is going to be d E sub r. And I could have the same thing going on up here. I could say that I have something like this, which would be E sub theta. And I could then have E sub theta prime. And what's the difference between those? D E sub theta, right? And that looks an awful lot like the figure that we drew in the normal tangential. So I won't belabor it anymore, but this is going to then give way to the derivative of the unit vector in the r direction is theta dot E sub theta. That shouldn't surprise us. And the derivative of the unit vector, eventually we will need this when we get into the acceleration, but the derivative of the unit vector in the theta direction is going to be equal to theta dot in the E sub r direction. And this is going to be negative, because if we look at this, this is actually in the negative r direction, isn't it? So this dE sub r is in the positive theta direction. This dE sub theta is in the minus r direction. So that's why we have that negative sign there. Okay, did I get that right? Yep, I think we're good with that. So with that, I can come down here and talk about the velocity and say that the velocity, so r is pretty straightforward. We'll put a box around that. Then the velocity, this expression doesn't do much good because I got to figure out, I got to substitute in for the e sub r, the unit vector, the derivative of the unit vector. So if I do that, I get the velocity is equal to r dot. I should be able to come up with that in the e sub r direction. There's no problem with that term. Plus, then when I substitute in for this thing, what are we going to substitute in for that? Theta dot in the e sub theta direction. So I'm going to come up with r theta dot in the e sub theta direction. So this is why in here for the exams you'll have a 3x5 card for the exam. I start to put equations like that on there. It's hard to remember. Let's see, is that r dot or is that r double dot? But here we have the velocity in the r direction as r dot, which makes sense, okay? As the distance r is changing, we're going to have some velocity there. And then we also have the r theta dot. Now you might say, well, we just learned in the tangential, the normal tangential, that the velocity only had one piece. Yeah, but I have a different coordinate system now, don't I? I've divided it up differently. So it should not surprise us that this has two pieces because we're looking at it in a different coordinate system. Do the units work on this? R dot is going to be, let's say, distance per time. R will be distance, and what's theta dot? Radians per time. So if you take the distance, let's say feet, and you multiply it by radians per second, that should be what? Feet per second? So that r theta dot term works out. So there's our expression for r. There's our expression for v. And the acceleration is particularly challenging. Let's look at that one. Maybe we'll say the acceleration starts out pretty cleanly at v dot. I take the derivative of v. We've talked about that. So let's see, with the chain rule, what are we going to have? I got to break up this first one, so I'm going to have r double dot, the derivative of r dot in the e sub r direction, plus r dot e sub r dot. So that's just the derivative of the first term in the velocity. And then I'm going to have to add to that. Let's see, if I look at this one, I really have three things multiplied together, don't I? I have that times that times that. So I've got to use the product rule a couple times there. So I'm going to have r dot theta dot e sub theta plus r theta double dot e sub theta plus r theta dot e sub theta dot. Okay. So this piece comes from the first term. These three terms come from the second term because you have a product of three that you have to deal with. So there shouldn't be any problem with this this one, r double dot times the unit vector in the r direction. This one is going to be trouble because I've got to substitute in what? Right up here, right? So I'm going to have theta dot in the e sub theta direction. And let's see, that's no problem, that's no problem, this is a problem. So I'm glad we did this one because I'm going to have to substitute in there. What do I have to substitute in there? Minus theta dot in the e sub r direction. So if I collect up the terms, I've got an e sub theta term here, I've got an e sub r, e sub theta, and e sub r. So collecting those up, I can say that the acceleration is equal to r double dot, I looked at that one there, minus, then there's the next e sub r term, minus r times theta dot, and then I have another theta dot there, so that'll be theta dot squared. And this whole thing is in the E sub r direction. Plus, then I need to come up with all the E sub theta terms. What do I have for E sub theta? This is the first one, so that'll be, let's see, that's going to be r dot theta dot. Do I never have another r dot theta dot? Yeah, right there. So I will have 2 r dot theta dot, because I have an r dot theta dot there and I have an r dot theta dot there, so 2 of them. And then what's the other one? The last one is right here, r theta double dot. And this whole thing is in the E sub theta direction. Excuse me. Now that's definitely worth a box. Let me double check, make sure I got all those right. Yeah. So you got a couple terms there. A little more complicated than the normal tangential because we're looking in different directions. Probably something you definitely want to put on your index card as you start to prepare for the examination. Well, what we'll do when we get together next time for lectures, we'll look at some examples where we get to use this. There's some kind of cookbook examples where we're given r and theta and we just go through the differentiation a lot like a math class. And then there's some more problems where we kind of have to tear this thing apart and really wring all of the value out of it. So we'll look at a couple of those examples when we get together next time and go from there as we finish up polar coordinates or cylindrical coordinates, however you want to think about it. Take care till then.